All right, so we're starting off today with the Mott problem doesn't show why the wave becomes a line, but rather why the line is not a wave. Um, so, um, the Action Lab is a YouTube channel, right? They made a video on this topic, on the Mott problem, right? So I recommend you watch that video for context, because this is what I'm kind of basing this off of. And this is what kind of sparked this, because I didn't know. Like, there's just certain things that I don't know that this is what we think. And after seeing it, I'm like, what are we doing? That's all I can say. Anyway, so basically watch that for context, and then what I'm talking about will make more sense, because I have some photos here from that video. Because one thing I really like doing is taking quick like screenshots while I'm watching like a video, so that I have like some extra context as to what I was looking at, what I was thinking when I was watching these videos. Because a lot of times I'll watch a video and I'll be like, that seems wrong. Call it hubris or whatever, but yeah. So these are particles. Right. So getting back to it, the Mott problem doesn't show why the wave becomes a line, but rather why the line is not a wave. These are particles, and the wave function is the probability of its location. When a particle is surrounded by other particles, they are affected by each other, limiting their probability, right? When the probability of its direction are lines, there are limited paths to travel as probability is reduced. So what I'm saying is that this is what's established in the Mott, like with the Mott problem, is that the more particles or more atoms or whatever are there, the more restriction there is on the paths and the direction that these like particles can be emitted by decay, right? Like, so this is about like alpha particles being emitted, like radiation, right? Radioactive materials in like a cloud chamber, you can watch them. And this was a big deal at the time before, this was solved. Basically, I think it was Einstein proposed, like, why are they straight lines if this is a wave? Shouldn't it be a wave? And this was like a big question. And then this was the solution to it, was this equation that could prove that the more particles there are, this results in, like, the more particles surrounding it, this results in, rather than it being an equal wave distributed out in every direction, it gets limited to single straight paths. Here's the thing. That's so dumb. I'm sorry. It's just dumb. It's just dumb. What's happening there is the wave itself was always just a probability. It's just a probabilistic. It could go in this direction, so we account for it. That's why there's a wave distribution. This is the probability of where it goes. That's what the wave distribution is. It is not a physical wave. It is not in all of those locations. It is just, it could be in all those locations. There's a very, very important distinction there. It's not that it is everywhere. It's that it could be everywhere, right? There's a potential chance for the particle to be in all of this location, right? And so we have this wave spreading out, because it could be anywhere there. We don't know, right? We don't know for certain until we do, right? And that's when we see, I keep doing it. That's when you keep seeing the lines. That's when you see the lines shoot out, straight lines, as if it was a particle, even though it's a wave, right? It's not a wave. Its probability is a wave, but when there's more particles around, there's points that get canceled out because it's like, okay, well, it's not going to go straight through this particle, so the odds of it going straight through there, okay, well, it can't go that way, so it's not gonna take that path. It's gonna go this way instead, right? So now there's a free space here, so it can go this way, right? And so it just happens that all the paths start to get reduced, right? And there's still tons of paths because just how tiny atoms and these radioactive alpha particles are. It's not like there's nowhere for them to go. There's plenty of open space. But so naturally, as more particles fill up the space, there's less space to move, right? And so you see this straight line instead. But we think that, oh, well, the wave is just kind of collapsed, right? But I don't think that that's what's happening, all right? It collapsed because the probability is now 100% it went that way, right? And so, this is just proof that it is, in fact, a particle and not a wave, as a wave would still continue out in every possible direction, just separately. We wouldn't see one streak, but a ton of them. We have just tried so hard to make this theory work, and we slapped the decoherence phenomenon onto it on the end to make it work. So what I'm saying there is, I don't know if you've seen that meme with like the flex tape thing where they like slap on like the tape, slap it on and you're good, right? Well, they went decoherence and just it's good, right? And that might be a dated reference, but I just think it's funny because that's pretty much what they did, right? It's like, oh, you got this massive hole in your bucket or something. We're good. Don't worry about it. But the problem is there's still a hole in your bucket, right? Anyway, so before decoherence, right? The quantum wave of the alpha decaying particle expands out in every direction equally, so to say. But as particles start to show up, we call this decoherence, where it no longer behaves as a wave because there's other particles around. And since there's other particles around, it now behaves more like a particle and forms into distinct lines of paths, because the probabilities cancel out and all these things. And it just so happens that, it ends up as a straight line. Who would have thunk that? That doesn't make sense, though. To me, that doesn't make sense. And if it's truly dispersing out in every direction, then when it's doing so, it should do it all equally all at one time. And so it shouldn't decohere into a single path. It should expand out in every path in a straight line, if that's how this works, right? But it doesn't do that because it only chooses one path because it's only one particle with one actual result. There's an infinite number of results possible, therefore the wave function accounts for them, and that's why the math works, because we are accounting for all possible things with the wave function. But that is not what is actually happening. We are just predicting what we can observe with this probabilistic function. What's actually happening is a single outcome. And we observe the single outcome whenever we try to observe it, whenever we try to see, hey, what's going on under the hood. It is always a single outcome because that's all that's actually there. We just have a probabilistic framework built so that we can account for the unpredictableness of this outcome because we don't have enough data. There's not enough data to know what will happen. and we think that it's not possible to predict it. And I don't think that's true. Maybe just not for us, which you could say, well, then it's not possible. And it's like, well, just because we can't predict it doesn't mean that other particles would not be able to know. Not relax. All right. So anyway, so basically this solution is not a solution. It's not what's happening. And deep coherence is just an excuse. It's not I don't know if there's really a good logic behind why that happens. Like, it doesn't make sense that if it's spreading out in all directions equally, that it consolidates all on one point. The only reason why that makes sense is if it's probability and 100%, it's right there. That's the only way that makes sense. But if that's the case, then it's not actually a wave at all. It's just a particle. Which is important because quantum, like, all of the quantum world is built on waves, and everything's actually just a wave. Its physical thing is just a wave, and that's just, I don't think that's right. I think you're wrong. I think that that's dumb. So, anyway, okay, so now we're gonna go into some speculation here. So I have, okay, this is, I think this was an Astrum video, talking about maybe it was either an Anton Petrov or an Astrum video, but they were talking about these galactic filaments that are in the Milky Way galaxy. We observe these filaments that are these really long structures that are kind of like just long, stretched out, thin lines in our galaxy. And so we don't know exactly what these come from, but they're huge. They're like hundreds of light years long, I think. And they're just kind of there, and we're not totally certain on where they come from. But I think now this is potentially severe abstraction here, but I have some images of, like in a cloud chamber, and these are from that one video, right? This is what it looks like when these alpha particles are getting launched off, right? And that's still the alpha particles. And then, not really the closest image there, but you can start to see these filaments. And then this image and this image are the same thing, just at different, these are all the same thing at different like wavelengths or something, different exposures. So all these like streaks that are going through here, the black and white streaks and stuff that are flying through, all of those are those filaments that they're talking about. And a potential theory here is that these filaments are basically caused by alpha particles on a scale that is beyond potentially our comprehension, right? So to us, this would potentially be quote unquote dark matter. And or potentially not. I don't know. We may not be able to see this. And I know that sounds ridiculous. So maybe we can see it, but when we look at it, we don't see it as a collective body. We see it as, a bunch of smaller things. But I'm not totally certain. But I think that these could potentially be alpha particles streaking through our galaxy, through all of the, we can see these alpha particles launching off because they're in this cloud chamber where there's stuff for it to react with, where there's tons of galactic dust, right? So potentially that could be it. I mean, that's just speculation here. I don't have any other good evidence. I just think that it could be that. And I think that is interesting if that's the case. And, and if it's not that, there's a current theory right now where it's, That's not the theory, obviously. But I think if it was that, would be interesting, would be cool. And so the galactic filaments we observe may be alpha particles of the galactic scale flying through dust clouds, like in that of the cloud chambers, so that they are made visible to us. Them having magnetic fields. Oh, this is another thing. So the filaments are. We've observed them, and from our observations, they have strong magnetic fields or something along those lines. They're magnetically charged. And so, to me, this makes sense with my theory because as a particle flies through an area, right, it kind of creates a void behind it where there's less energy, and this lack of energy results in a magnetic field. And so I think that it would make sense that these filaments are magnetically charged, because if they are these alpha particles streaking through, then there should be a magnetic field left in its wake. And so I think that would make sense. But them having magnetic fields makes sense with my theory that a particle flies through space. As a particle flies through space, it reduces the energy in its wake, causing magnetic waves and then a magnetic field to form. Lots of energy orbiting in the same, lots of energy in, and then resulting in, lots of energy orbiting in, and then resulting in high energy emission also makes sense with my theory. And so, as well as the radio, hold on, let me just read through it and figure out what I'm talking about here. As well as the radio bubbles above and below the galactic plane, as all scales of celestial bodies do this, and it might actually highlight the fundamentally different energy being released as it is ejected outside the galactic plane and no longer follows the fundamental theorem of algebra, where an object shouldn't be able to escape the complex plane. Okay, so that part ties back to a video the YouTubers called 2Swap. They did a thing about like the quintic formula, and when I found this video interesting. Do I totally understand what's going on? No, because math is not my strong suit. But this quote-unquote fundamental theorem of algebra basically says that when you have like when you have a certain function, I don't know, it's maybe like two terms. It's not, I don't think it's, I'm probably going to say it wrong. Watch that video. And so basically when the system is set up, right, there is, in this equation, all the roots, all the solutions to the equation fall on the complex plane. They cannot, there is no way to get a solution off the complex plane. And so this is important because I think it also applies to why why a lot of galaxies appear to be, disks. They appear to be relatively flat. And I think this has to do with this equation and the fact that, the fundamental theorem of algebra or whatever. So when things enter into the system, all solutions are on this complex plane. So when they come in to no matter what you enter with, you end up somewhere on this complex plane, eventually, right? And so that, I think, is a part of why this complex plane forms, where we have this galactic plane where it seems relatively flat, right? And so I think that that's interesting in itself. But the fact that we have what I was talking about before about these high energy, like a lot of energy swirls in, right? We get this strong energy, and we think that the current thought for where these filaments could come from, that doesn't have anything to do with my theory of what's it called? Alpha particles, is that a lot of energy, must have congregated all at one time, and it resulted in a really strong outburst of energy. And this really strong combination and outburst of energy is like, as it ripped around, like it left off like these kind of like strands that slowly stretched out. I don't think that that's necessarily it, because the way there's the differences in sizes and positions and stuff. I think there's just way too many of them for it to be that, now that I'm thinking about it. But that is a potential proposal of what it could be, right? But I think that the fact that a lot of energy kind of balls up and then gets, shot out makes a lot of sense, because when you have these, excess energy is brought in, excess energy, when something bonds or combines together, the excess energy gets released out, right? And so we should have these large emissions of energy, right? And going into, we have, dark energy, and then we have matter, and then we have dark matter, right? And so looking at a galaxy, we look at our galaxy, and we have these massive radio bubbles or whatever going up and down out of our like galactic plane. And so to me, this is really interesting and potentially shows that, things enter into our, complex plane or galactic plane from, like, I don't know, just outside of it, we'll just say. I don't know the specifics of where, right? But the energy, like, it gets transferred, it gets transferred from the complex plane into, like, the next level. Like, you have to watch this video for what I'm saying to make sense. You have to watch this 2-swap video. I'm sorry. But you, like, the energy is in the complex plane, and then eventually it is allowed to, like, as I said, there is no solutions. But the solutions are just the roots to the equation. That doesn't mean that there's, like, it just means that all equilibrium points are going to be on the complex plane, right? But even though all the equilibrium points are on the complex plane, that does not mean that energy and objects cannot be elevated to another degree, right? Add in another root or another unknown or another root or whatever to the equation. So instead of it being, 3 variables or whatever, it's now 4. You get is quadratic the right word? I'm not sure. A quadratic equation? Probably not. I don't know. All right, watch the video. I'm telling you. And you should watch it, because I'm going to make another video that's actually about it as well. It was an interesting video. Anyway. What's potentially happening there is we are observing dark energy being emitted here, and all we see is the radio waves of it, because to us, it doesn't have, it's too massive for it to, I don't know, I guess it's too massive for us to observe it properly. Because its energy is no longer bound by velocity, right? And so, since its energy is no longer bound by velocity necessarily, like it is in our reality, things have relative energy, and so they have a mass, but they also have a velocity, and those things together is what gives things energy in our reality, in our universe. And so dark matter gives off, relatively low energy, if any energy, right, that we observe, because it's just, like, it's hard to explain, because dark matter is potentially just like, on a scale that's like above us. And so when we look at it, we see it doesn't look connected. It looks more spread out and like gaps in it, right? It looks like it looks like, just like as we observe, we just have this big radio cloud, right? And it's like, what is that? What is that? What is that? And to me, it's just the residual. It's all that we can see of it, because it's not giving off a lot of energy it has a lot of energy, but it doesn't have a lot of energy to us, right? Because it would be like looking at something that's stationary, right? You look at an object that has a lot of mass, you look at a heavy weight, and technically it has a lot of energy because it has a lot of mass, but it's completely useless, right? You do not look at a stationary object and go, wow, look at all that energy. Because to us, that energy is not useful. It's not observable. We don't look at something and just look at it, we're like, wow, that's got to have a lot of energy in it, right? Without knowing its density, you have no idea how energetic it really is. You have no idea how much energy is in it, because it's just not observable to us. It's a combination of velocity and mass that makes the energy of things observable to us. And majorly, it's the velocity. And these things are just moving. They're just moving at time scales that are different to us. And they are so dispersed because they appear to, like, they're a solid thing, but the reality is that nothing's solid. I don't know. I'm getting too into this for this video. So if you understand what I'm trying to say, then yeah. But, basically, radio bubbles above and below, and potentially like supernovas kind of look like these big balls of nothing as well. Like looking at this as like these big balls of nothing from supernovas and stuff. And I think that that's interesting, but I think I'm going to just leave it here. So yeah, peace out.